Hey, welcome back to your favorite calculus class. We're going to look at Rolle's theorem as well as the mean value theorem in this section. Rolle's theorem states that, and by the way, this is named after the French mathematician Michel Rolle that lived in from 1652 to 1719. This guarantees the existence of an extreme value in the interior of a closed interval. So the requirements are uh, with Rolle's theorem. First of all, f's got to be continuous on the closed interval, and it's got to be differentiable on the open interval. If you got two y values that are the same on those endpoints, then there must exist a c such that f prime c equals 0, right? So for example, you can see that quadratic there where from a to b, right, and we've got this quadratic, so we know it's continuous on the closed interval. We know it's smooth and continuous to be differentiable, right? So it's differentiable on the open interval. And then we've got these y values that are the same, f of a equaling f of b. So this is saying there's guaranteed there's got to be some c in here. It looks like it's right there, where f prime of c equals 0. Here's another one over here. You got f of a equaling f of b. This is smooth and continuous, so it's continuous. It's differentiable, right? So it meets the requirements there. You notice there's actually multiple spots where f prime of c equals 0. So that's what the Rolle's theorem says. Now, we can't drop this differentiability requirement, okay, because you're not going to have a horizontal tangent. You won't have a c value such that f prime of c equals 0 because it's not differentiable there. Okay. All right, let's do this one here. We've got this function, and whatever this uh, quadratic looks like. It says find the two x-intercepts. So uh, that's your a and your b, okay, in Rolle's theorem, and show that there's a c in there, or f prime of x, or some x value in there at some point between the two x-intercepts. So first of all, let's find the two x-intercepts. So 0 equals x squared minus 3x plus 2. So it looks like 2 and 1, right? So a 1 and a 2, like I drew here. You have a same y value, so that's your a and b, right? Now remember, Rolle's theorem states um, let f be continuous on the closed interval and differentiable on the open interval, then there must exist a c in that interval such that f prime at c is 0. So our a and our b here is from 1 to 2, right? We're just looking from 1 to 2. There's got to be a c in there, and we can see it right there. It's right there. We just don't know where it's at for sure, right? We can see that f prime of c equals 0. We know it's continuous, it's quadratic. We know it's differentiable, smooth and continuous, right? On the open interval as well. So, well, let's find the derivative, and let's find where this c value is. The derivative, so I'm taking the derivative, 2x minus 3. Where is the horizontal tangent? So where is f prime equal to 0? Where is the slope of the tangent line? 0. Oh, it's at 3 halves. So right there at 1.5, at 3 halves, that's our c value, right? So by Rolle's theorem, sure enough, there is a c value. In this case, we're calling it an x value in between 1 and 2, such that f prime of c equals 0. There's a little better picture of it. All right, the mean value theorem. This one's saying you've got those same conditions that Rolle's theorem had in that f's got to be continuous. In fact, I always like to write it out. If f is continuous on the closed interval from a to b, and differentiable on the open interval a to b, then there must exist a c in this interval from a to b such that f prime of c is equal to f of b minus f of a all over b minus a. Let's see if we can make it. Let's make a picture of this and see if we can make sense of it here. Okay, let's say I've got, I don't know, some thing like this here from a. I'll go to b here. Okay, here's f of a, f of b. Now, notice right here we've got y2 minus y1 over x2 minus x1. We got the slope of the secant line, right? If I was to draw that, okay, there's the slope of the secant. So this is saying there's some c value within this interval from a to b, as long as the function's continuous and differentiable, continuous on the closed, differentiable on the open. There's got to be some c value in here such that the slope of the tangent is equal to the slope. So there it is. That's where that c is. Slope of the tangent is equal to the slope of the secant, f of b minus f of a over b minus a. You see how those are parallel? Same slopes. Okay? So let's do an example with that. Oh, there's a better picture. Forgot about that. Given the function f of x equals I'm going to actually write it negative 4x to the negative 1 plus 5. Okay, so I'm going to rewrite that. Find out all values of c in the open interval from 1 to 4 such that. All right, so we've got this function. Let me kind of get a picture of this thing. If I plug 1 into the function, 5 minus 4 over 1, I got 1. If I plug in 4 in, so I have 1, 1. I plug 4 in, 5 minus 4 over 4, I got 4. Off of it. It's up here 4, right? And kind of draw this. Got, I don't know, I can't draw this very good, but anyways. 1, 1, 4, 4 up there. Okay. Anyways, we're trying to find the c such that, where's the c at? Right? Like where's the c such that the slope of the tangent is equal to the slope of the secant line, right? That's what we're trying to do. What c value is that, right? You notice we even have this written out. What's the c, right? What's the c value? Where does f prime of c equal f of b minus f of a over b minus a? This is our a, that's our b, the 1 and the 4, right? From 1 to 4. All right, where's the slope of the secant equivalent to the slope of the tangent line? Well, let's do it. All right, let's go. Let's find the derivative first. Let me use x here. So I got negative 1 times negative 4. I got 4x to the negative 2. Derivative of 5 is 0. So f prime of x, or f prime of c, right? We're finding the c, but we'll just work with x here. It's 4 over x squared. Okay. Now let's do f of b minus f of a over b minus a. In other words, f of 4 minus f of 1 all over 4 minus 1. Well, when you plug 4 in, right, to the original function, you get 1. When you plug 1 in to the original function, you get, oh, I'm sorry, when I plug 4 in, I get 4. Sorry about that. When I plug 1 in, I get 1. Okay. this is supposed to be equal to f prime of x. So this is equal to 4 over x squared. So this becomes 4 over x squared, right? X is our c, if you will. 3 over 3, so 4 over x squared equals 1, whereas x squared equals 4, plus or minus 2, but we're only looking between 1 and 4. So it's got to be the 2. 2 is our c value, if you will. That's where that occurs. Okay, here's a little picture of it. See right there, 2, slope of the tangent is equal to the slope of that secant line. Okay. All right, find the value or values of c that satisfy the equation, the conclusion of the mean value theorem for the function, and the interval. So again, the mean value theorem, if f is continuous on the closed, differentiable on the open, what c value, f prime of c, where's the slope of the tangent, equal to the slope of the secant line. Okay? Alright, let's go ahead and find f prime of x. So we got 1/2 x minus 1, now it's to the negative 1/2, derivative of the inside is just 1. So that's 1 over 2 square root x minus 1. There's our f prime of x.
I can learn to understand you much better if I can get familiar with the way you talk.
Don't do that, computer. Alright, now that's our f prime of x, right? So that's right there. I'm not using c, I'm going to use x here. Equal. And we're going from a to b, from 1 to 3. So f of 3 minus f of 1 over 3 minus 1. Plug 3 into the original function, right? The original function, so I got square root of 2 minus, plug the 1 in, square root of 0, 0, over 3 minus 1. So I got square root of 2 over 2 is 1 over 2 root x minus 1. So I have, if I get rid of that 2, notice the 2's cancel there. So I got 1 equals root 2 times root x minus 1. So I got 1 equaling root 2 times x minus 1. 1 equaling 2x minus 2. Square both sides there. Add 2, add 2. And we got x being 3/2. Yeah, so it looks like for this, if I was to draw a graph of this, it goes like that. So from 1 to 3, like here's slope of the, oh come on, here's the slope of the secant, and at 3/2, so 1.5 of 3/2, slope of the, oh my goodness, it drives me crazy, 3/2, slope of the tangent is the same there. Okay? For that square root function. Awesome. Mean value theorem. Alright, does the function satisfy the hypotheses of the mean value theorem on the given interval? Well, first of all, it said the mean value theorem, if f is continuous on the closed interval, differentiable on the open interval, then there exists a c in that interval such that f prime of c equals f of b minus f of a all over b minus a. Right? So for tech issues there. So for this here, we got the f prime of x equals 2/3 x to the 2/3 minus 3/3, or 2 over 3 x to the 1/3. In other words, 2 over 3 third root of x. Right, here's our f prime of x. Okay. So now the question is the function continuous? Is continuous over the interval from -1 to 8. In fact, let me show you a little graph of this thing. All right, we got this thing's continuous, but notice, and let me come back to this. We can't have x being 0 because the derivative function's undefined. It's not differentiable. See that at an x value being, oops, this thing let me write. Come on, let me write. If our x value is 0, right, we've got a problem. We've got a problem. You can see it there. We got the sharp point. So the function is, yes, continuous, but it's not differentiable. Right? It's not smooth and continuous, right? We've got that sharp point. So it doesn't meet the requirements to satisfy the mean value theorem. So there's no guarantee that there's an f prime of c equaling to f of b minus f of a all over b minus a, for the a and b being from -1 to 8. Okay, that's it for today. Thank you so much for listening. That's Rolle's theorem and the mean value theorem. See you next time.